No matter where you are now, Asia, Europe, North America, morning, afternoon, or evening, I hope you and your family are safe, healthy, and happy. I'm Christine Sang, President of Waterloo Filtration Institute. Before we start, I would like to acknowledge our distinguished speakers and the panelists, as you can see on the screen. Thanks for their continuous efforts and contributions to the clean air industry, and a fantastic program they put together for us today. I'm so excited and can't wait for their presentations. Next, I'm pleased to introduce our moderator, Mr. Mitch McCurry, Sales Director of Waterloo Filtration Institute. Mitch is a great friend and a colleague in the filtration industry with over 35 years professional experience. Mitch, please take over.
Okay. Thank you, Christine. I appreciate the introduction. We do have a very tight program today. And I just wanted to, you can see the agenda here on the screen. We're going to be allotting 10 minutes per speaker to go over their interesting information. So what we'd like you to do is to direct your questions to either the chat box or the question and answer box down at the end or on the bottom of the screen. And what we'll do is have a 20-minute response time at the end of this presentation. So that would be about an hour and a half from now. So without further ado, I just wanted to let you know that. The next slide, please. Our first speaker will be Bob McIlvaine. He's the president of McIlvaine Company, a publisher of market information and general knowledge source for our community. Bob?
Thanks. It's great to be here. In fact, you know, Kathleen and other people just input valuable information to me that makes the whole experience worthwhile. And in fact, we are documenting now a great deal of information that viruses being created, being aerolized from the floor, from clothing, and most importantly, we're finding that the inefficient masks can become aerosol generators rather than capturing and sequestering the large droplets. And so the bottom line, along with all the evidence now that the virus is airborne, means not only is the virus airborne, but even the coughs and sneezes eventually are probably airborne, and a lot of the coughs and sneezes that end up on the floor are again airborne, and on and on. So our industry, the filtration industry, is now front and center to solve this problem, and I think that it's time for the epidemiologists and other people to step aside and for the filtration industry to solve the problem. That being said, we're starting from a base of about $100 billion split, as you can see here, with mobile being the bigger segment of the market. If we could go on to the next slide. If we have a reactive filtration industry, the COVID virus is going to continue to do what it's going to do. And when you have instructions that about wearing, you know, any mask is okay, and social distancing when virus clouds can travel for large distances, you're going to have an industry that's going to be waiting for herd immunity. And so on a reactive program going forward, whether it's liquid filtration or any of these other, or certainly on mobile, there'll be a lot fewer cars sold and so forth. So with a reactive filtration industry, you're not going to be even back to the $100 billion level in 2021. However, the proactive program, which involves the filtration industry, can result in hundreds of billions of dollars, and should result, because this is the way to solve the COVID problem. So we have a tremendous opportunity in front of us, and I think really an obligation, because I think it's pretty clear that the filtration industry is the way to solve this problem. So we go on to the next slide. So we have quantified some of these things as best we could in terms of what will mean in terms of increase in air purifier sales, masks, and respirators. We believe everybody, 3 billion people around the world, should be wearing an efficient mask every day. And of course, you do need the disinfection and wipes and monitoring, et cetera. So the reactive program, decisions are left to governments, and just as I said before, the filtration industry has to step up. Let's move on to the next slide here. I'm going to kind of skip through some of these next few, because I do want to focus on the fact that the inefficient masks will be aerosol generators, because I think it's very important and something nobody's addressed in the filtration industry should. So I'm going to, but basically the point I was going to be dwelling on in more detail than I need to, I think, is as the filtration industry, we are the one industry that can look at the world as a whole, a big clean room, and understand how to take the concept, which is increasingly popular in the clean room industry, of more efficient space within less efficient space within less efficient space. So it's one, I think it's interesting to look at it as one big clean room. And we just did a Man and Hummel interview a few days ago, and they're putting these filter cubes out at traffic intersections and so forth. So I won't belabor that point. Let's go on to the next slide. And then, just kind of taking this point on through, food processors you can improve pork life and all sorts of things. So it's not just removing the COVID, but looking at the whole pork processing. And it turns out even the swine, the herds have viruses and things. So looking at the clean room from all the way from herds of pigs down to the pork plants. So gone to the next slide there. And then just carrying this on again, pharmaceutical clean rooms are gravitating to class 10,000 space and then class 1 space within it. And luxury hotels are putting in all sorts of different equivalents of clean rooms and elevators and so forth. So that's the last place I do want to stop for a second, though, is in the filtering process, in terms of masks and things like that, but in terms of the whole process, you have to consider what mask or what's the first filtration step on the transmitter, as well as in the recipient. So let's go on here. And essentially, looking at a clockwise or counterclockwise evolution or transmission of your virus, and ideally, you've got an emitter that has a very efficient mask, so he doesn't emit much. If you're going clockwise, anything he does emit goes into the HVAC system. It comes out of the HVAC system. It's diluted. Most of the virus is gone, but what's left is heavily diluted, and then it goes to the recipient, who's wearing an efficient mask, hopefully. But what happens if the flow is counterclockwise and it goes from the emitter back to the recipient? And that would be the next slide here. And we have various different calculations and theories and so forth there that obviously have a lot of variables and factors in them that would change. But obviously, if you're going from the transmitter directly to the recipient, you know, you get a much higher viral load. But the point I wanted to spend a couple minutes on is it's beginning to dawn on us that inefficient masks are aerosol generators. And a corollary of that is that any kind of a cough or sneeze is going to end up somewhere, and it's going to end up as a large droplet. And there's lots and lots of information about large droplets in the air and how they evaporate and small droplets are generated and so forth. And you take that same logic and say, if you've got a big droplet on the inside of a cloth mask, what's going to happen to it? Well, you're going to, we know the water vapor certainly is going to go through. Why aren't the viruses going to go through? And in fact, there's all sorts of studies now that people are puzzled why they take swabs on the outside of cloth masks and find out there's more virus than there is on the inside of them as a result of these coughs and sneezes and so forth. So, you know, I think we're looking at a situation where people have not considered the fact that just because something is coughed or sneezed and has an initial stopping point, that's not the end of it. It goes somewhere. And other studies show that viruses are dormant rather than dead. And once they are in the lungs, they are revived, which is the worst of all worlds. You know, you might be better off to have coming from a cough and be in the nose rather than to have evaporated and be small enough to get into the lungs. So I think it's just a huge need, and a lot of the people that, you know, that are on this conversation are going to be able to add to all this. But if it all turns out to be true, it's all going to rest on the filtration industry to solve this problem.
Okay. Well, thanks, Bob. I appreciate it. I'd like to introduce our next speaker, who's Kathleen Owen from Owen Air Filtration Consulting. She has been a member of ASHRAE for some time and has 35 years in air cleaner testing IQ. Kathleen?
Good morning. I did a presentation back, it feels like months and months ago, but previously on what ASHRAE was doing in terms of a response to COVID. So this is, today I'm trying to hit points that we weren't doing then, things that either have changed or that just have come up, but also some information to put things in context. We are still having the conversation as to whether COVID is actually infectious through the air. Many of us who've watched pandemics go through before and had them later discover that yes, of course they were, are very concerned that it will be, as for why we're talking filtration. So far there has been RNA found in aerosol particles over a pretty good size range, but RNA doesn't prove that it would grow in a person. So then we have the question is, well, does turning your HVAC on help or hurt? Early on, they were saying, turn your HVAC off, open your windows. Now they're saying outdoor air is good if your outdoor air is clean, but what you need is clean air, dilution air. And if you get that by opening your windows, great. If you're in North Carolina living near me right now, it's not going to happen. It's 100 degrees outside by mid-afternoon, or at least it feels like it. So if you're using the HVAC, though, you want the air that you're diluting with, that you're bringing in, to be clean. So you need to either have no sources in your house, which you can't guarantee, or your building, or clean the air with filtration. And by doing that, you're diluting it. Even if you don't have all of the virus particles gone, fewer of them means you get less dose. The thing that HVAC can hurt with is either moving the virus around the building or sending out gusts of air, causing the particles with the viruses in them to re-entrain, to get back in the air, or to move to places they might not otherwise have gone. So the other thing that has pushed that seems to at least be a much stronger since a few months ago is to remind people that if you have a contaminated area or an area you think might be, try to pull your air from the clean area toward the contaminated area and then into your air cleaner or out of your building. Don't have your COVID patient sitting on one side of the room and have your airflow intentionally pulling it past your healthy person. I mean, nobody would do that on purpose, but you have to think about that your sick person or your contamination source might not be obvious. So, but if you have a good idea of where it is, you can plan for that. I mean, move your place your people sit. Or your dentist chair is located relative to your HEPA machine. Next slide. Clearly, your best filter is going to be your mask. That's your source control that's up at your face. And obviously, you know, from the previous talk and from everything that we've been seeing, different masks make different influence, but it's still the thing that's up close to you and it's keeping a lot from you getting out. It also keeps some stuff from other people getting in. But then we get back to, you know, what's going on with filtration that isn't masks. ASHRAE is distinctly recommending MERV 13 or better, where you can take it, and there's a caveat that there's information on the website, and go look at it for recommendations for places that MERV 13 isn't appropriate. But this is the filtration issue that's being talked about the most. So if your system can handle it, increase your filtration efficiency because it will decrease your particles. Noting that a lot of people are trying to push to HEPAs. Remember that if it's badly sealed, you're not getting a benefit. You may have way too much pressure drop, but you can put a HEPA in an in-room unit and get that HEPA level filtration if you feel that you really need it. Some alternates that ASHRAE is recommending are the UV systems. If you can't handle pressure drop, UV can kill a lot of organisms. We don't really have proof that it works on the COVID-19, but it works on most other things if your UV system is well designed. So pay attention to the capabilities of the people who are selling you products. And another note, the good filter cleans your air. It doesn't get your surfaces. If you move up to a HEPA, that does not mean you don't need to wipe off your table. And that, yes, is a question that people are coming up with regard to particles. Next slide. HEPA filters in portable units avoid your HVAC issues, but it only treats the air that gets to it. If you put a HEPA in your living room, your bedroom may not have cleaner air. It might, depending on how well your HVAC is also circulating air. High efficiency filters other than HEPAs also do good filtration. You just have to think about how many times the air is going through that device. So think about your CADR, which is the clean air delivery rate that your in-room units ought to be able to tell you what it is. There's recommendations for 1 to 2 air changes per hour for an in-room unit, but it does assume you have other airflow happening in your building. And consider your placement. Don't blow the air at the floor and pick your dust that might include COVID back up. Next. The MERV and the other efficiency of your product should be considered. One of the things that I like to remind people is that if you have a 95% filter, if you run the air through that filter twice, or if you have 2 of them in a row, it's equivalent to 99.7% removal. And if you pre-filter, depending on the size of the particle, you get to take both of those filters into account. And yes, at 0.3 microns, a pre-filter standard like MERV 8 pre-filter probably makes no difference. But if you're looking at 1 or 3 or 5 microns, it could make a little bit of a difference. One issue that's come up, we knew it before, but it's being talked about more now, is the charged media filters drop off in efficiency. And the graph I've put up here shows the data from a project I did a few years ago, but looking at charged media filter drop off in real use, but then the efficiency being tested in the lab, because I've had some people say, no, this doesn't happen. So, well, at least here's one example of where it definitely did. The drop off apparently can take place really quickly, although I haven't found the citation for that, but it can take place over months. And I've been asked, does that change how often you ought to change your filter. And it's with many of these issues, it depends on what you consider your need to be, because one of the things that happens is once it drops to the bottom, it's not going to get worse. So it may be that your filter dropped to its minimum efficiency after 2 months, and changing it at 4 months instead of 6 months, that's not going to fix that problem. But traditionally, I've recommended to people to use a slightly higher MERV if they're really worried about that. But the other way to go is to ask for a MERV A, which is the output from 52.2, which is the ASHRAE test method, that will tell you how much your filter is likely to drop in real use. Alternatively, go to the ISO test method and ask for an EPM rating, because that takes into account the drop off as part of their standard test. Next. Again, at one point we were recommending shutting HVAC systems down. We're not doing that anymore. If you can go to all outdoor air and you've got clean outdoor air at good temperature, great. But if you've got forest fires, or you're next to the interstate, or it's 100 degrees outside, or in a few months if it's 2 degrees outside, use your sense and think about what is better for you and what you can accomplish reasonably well. They're recommending 40 to 60% RH if you can get it, partly for how fast the droplets shrink or grow, but also effects on the lungs in terms of if it's too dry, you can have the infection rates and can change. Low 70s Fahrenheit seems to be a good temperature range to have. I mean, good in the sense of lowering transmission, but the other side of it is any contaminant that you normally have in your building that you need to take care of, don't forget it could still be there. If you're generating particles from something in your building and you had to control it before, take that into account. Keep your filtration good enough to control your regular contaminants along with your COVID. And again, use your HVAC wisely. Next. Schools and universities is a huge topic, and they just updated the document. So if you haven't been to the ASHRAE website within the last 2 or 3 days and you're worried about opening up schools or universities, there's, I think it's 45 or 50 pages worth of suggestions, a lot of them not to do with filtration. There's a recommendation for flushing the building. If it's been closed all summer, open the outdoor air dampers up and run your HVAC just to make sure that everything that's in the air and might get back into the air has flushed. They're also recommending every day to turn the mechanical system on early. And if you're using outdoor air, open your windows, turn your fan on, but clean the air out before the students get there. Also, good idea to run it either when they're not in the room, like if they do go outside, or at the end of the day, just to clear out the air. It's an easy way to get a chance to filter your air an extra few times when there's not a source going. They're suggesting that nurses' office start or have filters, for example, a MERV 7 followed by a MERV 14. Again, temperature and humidity guidelines, they're trying to get some ideas of what the temperature and humidity will do in schools. Different ranges, trying to be realistic for time of year. They are also recommending HEPA or UV air cleaners in each classroom for people who can do that, especially if you don't have a decent HVAC. Minimum 2 air exchanges per hour, and pay attention to where the air is going and gusting and what it will change in terms of the room aerosol dynamics. Next. For homes, if no one is sick, that's generally your safest environment. We knew that before. It's still in the advice. Maintain your thermal comfort. That's pretty much the range that you want to be in now anyway. If you're in an area of the world where 90 is considered comfortable, you might want to think cooling it off a bit more. I don't know where that would be, but there is consideration that some places what we in the US think of as normal isn't. If you can increase your ventilation rate, in this case, ventilation means bringing in more outdoor air. If you are in an area where the outdoor air is good to bring in from cleanliness or temperature and humidity, And again, if you can, operate your in-room air cleaners as much as possible. Next.
Kathleen, we're running a little bit tight on time.
I'm sorry. With sick people, be careful. Next slide.
Sorry.
That's okay. This is my last one. Unless I put something in, don't remember. We have a new calculated PM, so particulate matter efficiency in 52.2. If somebody comes and asks you about it, it's based on a flat distribution, as opposed to ISO being one of two, either a high small particle or a high big particle. The addendum will be posted online within the next week or two, and then it will take effect. You can back calculate from old reports. I'm done.
Okay.
And I'm going to disappear.
Yeah, disappear. Okay. All right. I would like to introduce our next speaker. Is Sean O'Reilly from AAF Flanders. He is the Global VP of Sales and Innovation. Sean has also been in the air filtration business for about 35 or more years and is recognized as an industry expert in the field. Sean?
Good morning, everybody. Thank you, Mitch.
You're welcome.
Next slide, please. This might be a little bit dated, but I just wanted to show the industry recommendations that came fairly early with COVID. Around March, ASHRAE recommended a guideline to upgrade to MERV 13, minimum MERV 13, as Kathleen mentioned. And then also this discussion about whether the virus was airborne or not is still ongoing, but the likelihood that it is airborne, so we should behave as if it is. And then the CDC also basically endorsed what ASHRAE was saying. Next slide, please. So some of the early trends we saw, as again mentioned by Kathleen, there was definitely a huge increase in demand for MERV 13 filters, and we'll say MERV 13 with a question mark because of the discharging that again was mentioned. And a lot of need for upgrading of filter racks to accommodate higher grade filters up to MERV 16, and in some cases HEPA filters. These recirc units were mentioned, or negative pressure units. There's been an explosion of demand. Almost every week something comes across my desk of someone offering a version of an air cleaner or a negative pressure unit. Initially for the healthcare environment, but now more and more for commercial and industrial use. And of course, UV is not a new technology, but there's definitely been an increase in demand for UV technology. Next slide, please. Some of the changes we've seen in the filter industry is, more end users are ordering ahead of time in anticipation of longer lead times. I'm going to speak a little bit about that later. Air filtration is moving from, I love this statement, occupant comfort to life safety. So I think for the first time we're recognizing, high AQ has been talked about probably for a number of decades, but I think now it's definitely got more visible, and we've much more focus on air filtration, unfortunately because of COVID-19. And there's also capital improvement upgrades on filter racks and housings, as I mentioned earlier, same for UVC lights. So one of the biggest changes we saw, typically we'd see a MERV 8 pre-filter and a MERV 13 secondary filter in a 2-rack system or 2-bank system. Where you've single stage for those rooftop units, people want to upgrade from MERV 8 to MERV 13 minimum. And that caused a huge backlog in, from the media vendors. The markets increase. We see a jump of 10-fold increase in demand year over year for MERV 13 media, for the pre-filter at least, at 2-inch pleat. And just to re-emphasize again, the recommended minimal final filter rating is MERV 13 or better. So a lot of the media manufacturers, I think on the last call we had talked about, they've been asked by the government and to focus on developing or supplying masks for the PPE. This has caused a huge shortage in the industry worldwide. You know, we're outsourcing now into buying media from Asia and different parts of the world just to try and keep up. But one of the impacts is a price increase. You know, a lot of the media has gone up by 30–40%. So that means an increase in the unit price for filters. So it's an ongoing issue, and you know, we don't see any change this year just based on the volume of orders we have today. Next slide, please. So I think, you know, we're mainly talking about filter efficiency, but one of the considerations we should take is really supplying filters with a total cost of ownership. So, you know, because we have an increase in pressure, you know, you can use filters with a higher surface area, a higher effective surface area to mitigate that increase in pressure. So there's definitely a trend towards, you know, buying product based on total cost of ownership rather than price. So that's a good thing for the industry. You know, when we do go up to MERV 16 and above to HEPA filter, you know, you have to look at upgrading your fans or adding a, you know, an inline HEPA housing downstream with a fan to compensate for that increase in pressure drop. I just showed some images. Here's an image of a horizontal room air cleaner. You know, of course, they come in vertical as a mobile unit. Some of these can be mounted as in waiting areas, in reception areas, in schools, in obviously dental areas and in hospitals for both negative pressure and for room air cleaning. So that's all I had. I will add one last thing because Kathleen touched on it. I think it's very important when we talk about MERV 13 that it is a true MERV 13. You know, and a lot of the 2-inch filters are not behaving as 13 in real life. That efficiency does drop off quite dramatically. So it's something to be aware of. There's no real alternative. You know, when you go up to probably MERV 11 is the best you can get. True MERV 11 is the best filter you can get in real life. So that's something the industry is working on to try and mitigate. So thank you. Thank you, Mitch. Mitch, you're on mute. Yeah.
Excuse me, I'm sorry. I'd like to introduce our next speaker, Stephen Nicholas. He's an HVAC, air filter, and ventilation consultant. He's been in this business for over 35 years, and he was past president of NAFA. He is a certified air filtration specialist, CAF, and an NCT 2. Stephen?
Thank you. Good morning, everyone. My focus is going to be not what the requirements are that have been set forth. Kathleen Owens specified the MERV 13, the last speaker. Sean O'Reilly talked about the MERV 13 or higher. It's important to have the right efficiency, but equally, if not more important, is the installation. I'm going to talk about the installation. And next slide. As mentioned, the CDC, with the recommendation to ASHRAE, recommend a MERV 13 filter or MERV 14 if the system has the capacity to overcome the static pressure. Next slide. Going through an HVAC filter inspection, last speaker referred to them as filter racks. We call them filter banks. They're either a filter frame, as you see in the slide, where they're vacuuming out the interior of the frames, and the gasket has to be applied on the inside, covering the clip so there's no gap. When the install of the filter comes in, you will need to secure those latches, 4 of them per filter. Air hitting you in the back of the head, this is called an upstream installation. Technically, you really only need 2 clips, but we highly recommend 4 clips on each side of the filter, on all 4 sides, so they get a secure, tight seal forcing the air through the filter. So we inspect the gasket on the doors, on the frames, and on the filters themselves. Next slide. What we do to find leaks is we shut the unit down, lock out, tag out, all the lights are off. We have one individual go upstream, other downstream with a grid, and they scan the entire filter bank. And you'll see lights coming through on the other side where they're marked and identified. And after you identify the areas that need to be sealed up, you seal them up, and then you have a nice tight seal for the installation when the system is going to be in operation. The next slide. In order to practically measure the pressure drop, you need some type of instrument, a filter gauge. Dwyer makes gauges, they make Magna Helix, and they make the manometers using an inclined manometer going from 0 to 3 inches in pressure drop. The importance here is to check the pressure drop on the filter when it's clean and make a note of that. You want to determine when the filter should be changed out. You need to put this gauge in with the sensors in the right location. Check when the last calibration of the gauge has been dated for. You want to make sure the gauge is accurate in order to read the proper pressure drop. When you have a frame system, as I mentioned earlier, you'll need to cover the entire frame with that gasket material. We used a closed-cell neoprene gasket, the type they typically will put on a HEPA filter. Again, I mentioned 4 clips that are being installed correctly. Check airflow velocity. The airflow in the initial pressure drop will be based on the velocity. The higher the velocity, the higher the pressure drop. A note of importance is when you get a test report that they refer to, a real MERV 13 or real MERV 14, you're going to get an independent test report from ASHRAE. They have 7 flow rates. You want to make sure that the flow rate that you're running on your system is the same that the test report has been given. This pressure drop at the same velocity should be identical. There should be no difference if you're running 450 feet per minute across a MERV 13 filter and you're getting 0.4 inches static pressure. That should be the same in the test report as the same in the field. Next slide. You can see the slide is showing you a side access installation. You can see the door where the filters go up against the door. You want to make sure the door has a perimeter gasket. Usually it's a same type you use in your vehicle. When you close your door, it's a rubber, a specific rubber for HVAC. You want to make sure the door has a complete gasket around the door, and you want to ensure that the track length that the filters go end to end without a spacer. If spacers are used, that's the probably 12 inches, 10 inches, 8 inches, you want to put it in and permanently install it to avoid putting it in and out and causing, avoiding air leaks. So the way to seal up a filter in a side access, unlike the frame where you gasket the perimeter, use an HVAC gasket tape. You put it on one side of the filter, you pop in the other one, and they connect. This eliminates bypass between the filters in the track. Next. So to recap, it's all about installation. Think of the HVAC air filtration system in a commercial building, a hospital, anywhere in the industry. Think of that system, HVAC filter system, as the mask for the building. As mentioned earlier, if the mask isn't fitted properly and you don't have it sealed, you're not going to get the effectiveness that you're looking for, whether it's MERV 13, HEPA, or anything else. It's important to seal the filters. We check and calibrate the filter gauges and make sure that the gauges are working properly. We typically have a calibrated gauge that we go out and we will field calibrate our clients' gauges. For example, if they're reading 3/10 of an inch, my calibrated gauge is reading 2/10 of an inch, we will field adjust that to make sure that it's reading properly. Check initial air filter pressure drop, as I mentioned. What the velocity that you're running in your system and what you're reading for pressure drop should be identical to the test report that you get. Next slide. After the system filters have been installed correctly, you want to document pressure drop, schedule periodic static pressure monitoring. So what we do is we recommend that every month they take pressure drop readings and you measure it and you monitor it on a monthly basis, and you can effectively manage your HVAC air filtration system. That concludes my presentation.
Thank you very much, Stephen. Appreciate
Thank you.
it. Sean, I just wanted to make sure that since I was mute before, I wanted to say thank you very much for your presentation as well.
You're welcome, Mitch.
Now I'd like to introduce our next speaker. It's Kari Lukano. He's from, I don't know whether I pronounced that right or not, Kari. I'm sorry.
Yeah, that was close enough, thanks.
Close enough, thank you. He's from Fibertex Nonwovens. He's a business development director for filtration. He's had 35 years in chemicals and natural synthetic nonwoven manufacturing and applications in nanofiber and filter related industries. I'd like to introduce Kari.
Thank you very much, and good morning to everybody. Can I have the next slide? So I'm going to talk about a little bit of the existing face mask materials used according to the standards, and then some other materials used which are not exactly to the standards, and some new materials and standards which are coming in line, for example, in Europe. Next slide. So this is one comparison of the different type of materials to filter bacteries, and the bacterial filtration efficiency is basically the kind of the criteria how people are evaluating the efficiency of different materials against the COVID. And in top you see the surgical mask, and then you see all kind of materials in relation to the bacterial filtration efficiency. And you can see that, for example, vacuum cleaner bag, if it's a paper bag and you put it in your head, it can prevent the bacterial emissions, but of course you can't breathe through it. And then there's a various this type of civil mask materials which people are using all over the world, linen, cotton, and silk, and scarf, and these type of things. But typically the only materials which can reach the required efficiency are non-wovens on these various standards. Next slide, please. So these are the three types of materials used today which are actually meeting the standards. And the first is the single-use masks, which is typically, for example, the type 1 level 1 barrier in USA and in Europe. And these are electret melt-blowns. You see a little bit also this type of thicker SMMS products, which might be in some cases to actually able to reach the standard. And when I'm talking about reaching the standard, I mean that there has to be a certain bacterial filtration efficiency, particle filtration efficiency, and the breathability, what is required. The second type is the surgical masks. And on that range, there is most typically used electret melt-blowns. Also, we see on this category now more and more also nanofiber-based products. The third one is respirators, where we need the particle filtration efficiency. And on these respirators, typically the bacterial filtration efficiency is not actually in the standard, but in real life, they are the products which are used in the very critical hospital environment. And the main reason for that is really that since the particle filtration efficiency is clearly much more higher than the surgical masks, they also provide a very high bacterial filtration efficiency, typically over 99%. And again, the main products which are used on these type of products are heavier weight electret melt-blowns, and again, nanofiber, fine fiber in different forms are okay for this. Then in the marketplace all over the world, there's also now products which are actually reaching the bacterial filtration efficiency requirements, but are not actually filling the breathability requirements. And we see now that, for example, a lot of microfiber products in use already, either single use but also washable grades in the different weights. We also there's a lot of SMMS type of materials which are also filling the bacterial filtration efficiency but not reaching the breathability. Also, nanofiber and melt-blown composites typically either laminated together or sewn together, and these are usually consumed on this type of filter pieces used in the reusable woven masks, where you just change the filter piece every now and then and wash the frame mask continuously. Also, there is some products already made as well with the wet laid process, where you can use a little bit finer fibers to reach the quite a high efficiency on the bacterial filtration efficiency, but not reaching the breathability. And for example, in Europe, I just take this as an example that there is a lot of there has been a lot of increase in the melt blown capacity and the mask making capacity, but still the demand is so large that when the larger audience in the consumer side are starting to use these masks, there isn't enough material available in melt blown and nanofiber to provide everybody the protection, and therefore European Union is now launching a new standard in addition to the respirators and medical masks and single-use masks. Next slide, please. Where the idea is that since there isn't enough material available, that there is more options for general public to have something to protect themselves against COVID. And it's these devices are not classified as medical materials or as PPE. So there will be less restrictions when you are qualifying these products and so on, comparing to these official other classes. Next slide, please. So in EU, there will be these two new classes. So if you remember that the minimum requirement for the bacterial filtration efficiency, for example, for the surgical mask is 95%. And in Europe, there will be new two classes. One is 70% efficiency on bacterial filtration, and one 90% bacterial filtration efficiency. The limitation for the breathing resistance will be also not as low as in surgical masks. So it will be 70 pascals per square centimeter. So it is then acceptable that there will be less breathing materials for this category. And if you look roughly, just to give you an idea that what it means, that if you want to reach the 70% of the bacterial filtration efficiency, you roughly need about between MERV 13, MERV 14 type of filtration efficiency product to reach this bacterial filtration efficiency over 70%. And then if you want to reach over 90%, then of course you need more efficient filtration material. And as a summary, I think this is, at least in Europe, this new standard is coming because of the necessity of providing people more protection. There is, of course, there can be a lot of discussion, are these enough? But at these current circumstances, this is the outcome of the in the European Union. And I think if you look what we have seen, at least in Fibertex in the different parts of the world where we are also operating, like in Brazil, South Africa, the similar approach has been already adopted in practice. So we are producing, for example, spunlace products, which are providing this type of 70–80% bacterial filtration efficiency, not meeting the official standards, but anyway, used for the general public, since there isn't anything better available in larger scale. Thank you. That was all by my side.
Thank you very much for your presentation, Kari. It was very interesting. Thank you. Thank you again. I would like to remind everyone here of that we wanted to try and bring our questions through the Q&A box at the bottom of your screen. If you could do that, we would very much appreciate it. Our next speaker is Eric Fu. He's the Managing Director of Aimwell, Australia. He is one of the innovators in a new generation of powered respirators. In 2009, he co-founded PAFTech Australia and invented Clean Space Regulators, a low-profile powered respirator series. I'd like to introduce Mr. Eric Fu. Eric?
Can you hear me? Hello?
Yes, I can hear you now, Eric. Yes.
Oh, that's great. Sorry about that. It's messed up. Okay, good morning. My presentation is about PAPR on COVID-19. Next slide, please. So in this slide, it shows a typical use by healthcare workers for COVID-19 protection. It's a surgical mask or N95 mask together with a face shield or a pair of goggles. So they are quite effective to protect transmission via droplets. Next slide, please. However, there's an increasing concern about transmission via aerosol, which is the particles less than 5 microns floating in the air. So this is a serious issue for a lot of healthcare workers facing. Next slide, please. The issues with surgical mask or N95 mask is the protection is limited. And the key reason is the leak through the gaps in the mask with your face. And also, they're not very comfortable for prolonged use, for instance, to wear for a full day shift. And also there's other shortcomings. For example, if you wear goggles, you may have foggy mist in the goggles. And also you could have a compromised communication because the mask cover your lips and they can't read your lips and the facial expression, things like that. However, the main issue still is the protection level and also the comfort. Next slide, please. So PAPR basically is very strong at protection. It introduce or create positive pressure inside the mask. So it makes the protection more reliable than surgical mask or N95 mask. And also it has no breathing resistance, so you can wear that comfortably for quite a long time. Next slide, please. So this is the ASHRAE assigned protection factor table. In this table, you can see N95 respirator have a factor APF 10. And if you look at PAPR, it starts from 25 and up to 1,000, so very high. So next slide, please. Next slide. Okay. There's two categories for PAPRs. One is called tight-fitting PAPR. The protection can go up to APF 1,000. However, this kind of PAPR require fit testing to reach that claimed protection factor. Next slide, please. Next slide. Okay, another category is called loose-fitting PAPR. It has an APF of 25, still 2.5 times better than N95 mask. And the great advantage of this type of PAPR is you don't need to do a fit testing. You just grab one and use, very convenient. So we have PAPR can give you very good protection, but why we can't see a lot of used these days by healthcare workers. So there are reasons behind that, and there's a number of shortcomings associated with the PAPR are on the market. Next slide, please. Okay, the key thing we're looking for, or the issues we're facing now with current PAPR, is the weight, size, and noise. So normally they are very heavy, bulky, and noisy, so that prevent people using that very often. And another key issue is also the cost. Normally it's very expensive, so that keep a lot of application out of the question. Other than that, there is a number of issues facing PAPR. One of them is most of them lacking the exhalation filtration. So if you don't have exhalation filtration, you can't use that on an operation theater. Or if you're a patient, you can't wear that because you're going to spread the virus. Also, PAPR sometimes hard to clean or disinfect, and some are very difficult to use, troublesome. And also, they can muffle your noise, your speech, so make the communication may be compromised. Next slide, please. So having said that, there are progress in PAPR technology. One of the advancements is the flow control technology. The traditional PAPR, they have a constant flow. That means when you inhale and exhale, the flow is the same, the blower running at a constant speed. The new technology has breath responsive flow control, which means when you inhale, it provides you the enough flow you need. And when you exhale, it reduces the flow. So it saves energy, meaning you can have a smaller battery and the whole respirator can be more compact. Next slide, please. Another improvement is the wearability. So traditional PAPR are heavy, bulky, like this one from 3M Jupiter. So they have a belt-mounted PAPR at the back and then connected with the big holes and to your headgear. And the one at the right is a new generation PAPR called Clean Space Halo. It is a neck-mounted low-profile respirator, easy to don and off. So that makes it much easier to use than the traditional PAPR. Next slide, please. Okay, one of the key issues facing PAPR is the standards. So currently, all standards are industrial application based. For industrial application, there's a lot of dust and also require high physical exertion. So that requires the respirator bigger. So you need a bigger battery, bigger filter, bigger blower, everything is big. But in healthcare settings, it's different. There's not a lot of dust. There are a lot of viruses, not dust. So the conditions are different, and the standard need to accommodate to this different situation. So the future consideration is we need a new standard to account for light to moderate exertion, typically in healthcare settings. And there's also a discussion talking about incorporating ISO standards to 9/42 CFR Part 84, because it has different work rates to accommodate for different applications in healthcare settings. So hopefully, if all going to the right direction, we should see more PAPR use in healthcare settings. That's all I present today. Thank you very much.
Thank you very much, Eric. Appreciate it. I have to admit I knew very little about PAPRs before I saw your presentation. Thank you.
All right, thank you.
You're welcome. I would like to introduce our next speaker. He is Len Castellano. He is a chief engineer at Parker Hannifin Filtration's Innovation Center here in Tennessee. He has 40 years of experience in R&D and development, polymeric membranes, and a number of other areas within filtration. His expertise in leading development to novel materials for filtration, separation, and purification, and he also helps in the micro, nano, and ultrafiltration technologies. He is also an AFS board and corporate sponsor, vice chair. Len?
Thanks, Mitch, and thanks, Christine, for having me. I feel honored to be on this panel. I'm the rookie here, I guess, in air filtration. My expertise is mainly on liquid filtration and materials and products in that area. But being at Parker for the last, Clarkor and Parker for the last 5 years, I've gotten a lot more knowledge in air filtration. But so excuse me if I misspoke in some areas here. Some of the information I'm going to present are actually some information that comes from our prestigious panel and probably some people on the call. So bear with me. First slide, I'd like to, I thought I'd start this presentation with a current summarized snapshot looking at the patent landscape on air filtration. I use a search tool that we have access to here called Anography, and I looked at applications and patent publications from 2015 to current. Normally, I would do a bigger filtering exercise when I'm looking at doing searches, but I kept this one pretty broad. I did only look at the last 5 years, and I also looked at only active patents and applications. Unlike a standard Google search, Anography allows for semantic searching. So this means that I can tell the difference between filter air and air filter, which in a Google search, you wouldn't be able to do that. And they're two different things, obviously. I also use some variations on terms in case I saw any big discrepancies. As you can see, the data looks very consistent, regardless of the terminology. China obviously appears to be very active in published patents and applications, with the US, Germany, and the EPO all probably tied for second place approximately. There is a blip in the data for the US on air filters that I can't explain right now. It might be something I did, but I'll dig into that a little bit further as well. So it's going to be interesting to see how this trend continues given the current climate with the pandemic and emerging technologies like electric fuel cell vehicles that are coming into the foray. Further enhancements in face masks and higher indoor air quality needs. Also, you'll notice around a total of about 103,000 articles that published on air filtration. Next slide. I did my best to research the current projection for compounded annual growth, or CAGR, and I did note a variation in the projections depending on the source that you looked at. The CAGR itself was pretty consistent between sources from around 6% to 7% year on year, which I would consider good for large cap companies. Being the ultimate optimist, I listed 20.6 billion by 2025, but with the current environment and things like this continue, I think that could be a lowball number now by 2025. It could be possibly even double that, but that's what I found as the highest projection so far. CC&F stands for cartridge collectors and filters, by the way. I assume face masks and things like MERV 8 up to MERV 16 are included in this category, but I wasn't completely sure. Rising concerns regarding environmental health, coupled with reducing raw materials resources, are expected to fuel the industry growth. Interesting to note that the amount of non-wovens projected this year alone, just for air filtration, is over 700 billion tons. Next slide. We take a look at some of I looked at, researched on some of the corporate strategies will be in the future. We probably would see a continuing adoption of obviously a semblance of organic and inorganic growth strategies. However, I believe we will begin to see an increasing trend in partnerships and collaborations as the years came on, with mergers and acquisitions emerging as popular methods, really popular methods to be capitalized on by vendors that find very low barriers to entry into the global market as the years go on. Next slide. Legislation that is currently in place and the changing focus from Europe and the US concerning climate change is really driving air filtration innovations to meet higher energy efficient targets right alongside the requirements for finer levels of separation. As you all know, the higher the pressure drop, the higher the energy requirements for a system. This becomes very evident in things like dust collection, gas turbine intakes, and exhaust. Of course, this drives towards more efficient use of energy is in direct contrast to increased filtration efficiency, the conundrum of filtration. Decreasing fiber sizes into the nanoscale region and innovations in material have become the major advances toward more energy efficient and finer filters, with nano eventually emerging as the technology to have the biggest impact on filtration. You probably heard previous slides, by driving down scale and enhancing filtration selectivity. Research continues on the academic and the industrial sector, which will drive future industrial growth. Increased demand for electricity will continue to drive the need for additional power generation plants, and hence the need for increases in air filtration products. Companies all around the globe are turning towards more sustainable alternatives and methodologies as another way of improving their competitive advantage and increase their revenues. On the same front, governments across the globe are collaborating with environmental organizations on developing standards for the control of harmful emissions. The implementation of strict government regulations to protect human health by limiting or eliminating airborne pollutant concentrations will further aid in catapulting this market. Next slide. One of the biggest factors that is contributing to filtration growth is automotive emission regulations that are being implemented right now on a global scale to reduce the discharging of carbon dioxide, sulfur oxides, nitrogen oxides, and particulate matter from entering the environment. Europe's emission standards, Euro 6, drives to reduce levels of harmful exhaust in mass-produced vehicles, both petroleum and diesel. India and China are gearing up to follow suit. New laws will hopefully bring a dire needed change in air quality. One caveat to this obviously would be the increasing trend that we're seeing in electric vehicles in both India and China that may have a slight negative impact on this market. We'll have to see. In the high-tech niche biopharmaceutical market, the United States USP 797 does provide standards to prevent harm to patients that may result from contaminated compound sterile preparations. Diligent monitoring and measuring are key to meeting air cleanliness levels. I see an increase in this area as well. Some good news on the horizon concerning emissions of carbon dioxide. Many companies are now responding to remove CO2 from the atmosphere or reduce their own CO2 output due to consumer pressure rather than confusing government regulations. The increase in the natural and shale gas industry, driven by the desire for clean energy, utilize large quantities of filtration to various contaminants produced by these processes as well. Next slide. In a previous slide, I mentioned how energy, especially being generated by alternative fuels, will continue to drive growth. For automotive, cabin and intake filters remove dust and other solid particulates that may be harmful to pistons and cylinders. Air filters can also enhance the air to fuel mixture. This could help to make the engine run more efficiently by minimizing the ignition problems, lowering fuel consumption, and reducing emissions. Engine air intake filters have changed in recent years pretty drastically. New emerging requirements mean that quote unquote standard or common are no longer just good enough. New powertrain technologies, an increase in efficiency, and the lowering of aerodynamic lines at the front of a vehicle, coupled with larger cooling systems designed to meet better fuel economy, will result in less and less room for air filters. Previously, I was just involved with designing an air filter for Volvo last year. It's amazing how they kept coming back, reducing the size of the filter and not reducing the requirements for air capacity or air pressure drop. So it's getting to be quite complicated. Indoor air quality is still a major problem in the mega cities in countries like India, Seoul, Beijing, and Stuttgart, to name a few, where really high levels of particulate pollution exist alongside large numbers of people. Interesting, cannabis and livestock are additional applications growing in interest in the need for filtration. The markets for marijuana and hemp are becoming legal for recreational use in a lot of other countries now, and more states in the US. And there are problems associated with the lack of filtration, resulting in complaints of, of the large odor and accumulations of things like mold and mildew on the plants, leading to product recalls. Next slide, please. So what do we think the future of air filtration has in store for us all? Well, I have to admit, I got a little carried away, and maybe I should have included 25 years as well in the opening statement on this slide. I would like to be around to see some of this, actually, and I don't think I'll be around in 50 years. Antimicrobials could eventually succeed. New developments are constantly being worked on. Dramatic results are always achieved in the laboratory, but only work marginally well in the real world applications. But I believe that in the future, these techniques will be perfected, leading to antimicrobial filters becoming more of a standard. I don't know about you, but I still get upset that I have to replace my own home air filters every 30 days. I have to believe that self-cleaning filters will also become commonplace, similar to self-cleaning ovens of today. It may be hard to imagine filters that can capture more than 99.999% of particles less than 0.3 microns, like a MERV 20 can. Fortunately, these sky-high ratings are really only necessary in the most critical or harshest of environments. But in 50 or 100 years, though, when possibly some of the hottest technologies make use of these materials, filters like this could be standard household appliances. And that's all I have today.
All righty. Thank you very much, Len.
No problem.
Very good. Thanks very much. All right, everyone. Now, I want to thank all of our speakers for joining and our panelists as well. We do have some questions now that we'd like to address with our panel, with our speakers and or panelists. So our first question comes from Samia Moore. Slide 14 for you, Bob McElvain. You had talked about various sizes associated with particle sizes associated with the numbers that you had on slide 14. Do you have any idea what those virus sizes were? Bob?
Yeah, I guess, am I unmuted now?
Okay.
Yeah. Yeah, the virus sizes are in the 0.12 microns, but it can be encapsulated in droplets that, could be 5 microns or much larger. There's a lot of information coming out now, for instance, in the Lombardy region of Italy, that they're finding virus on the air pollution particles, and this is happening elsewhere in the world as well.
These viruses find any way they can to get in, huh? So,
right.
Sure. All righty. Thank you very much, Bob. We have another question from Mr. Lucanon Kari. Your question is spun lace better than hydro-entangled for a barrier?
It depends on totally what type of fiber diameter you can find to use on those. So, the hydro-entanglement, typically you can make easier this type of washable products. So you can have different type of fiber structure or fiber composition in the product. The spun lace is very easy to make, at least the disposable products. Also some washables. On this certain bacterial filtration efficiency level, around this from 70 to 95%.
Okay. What's the major difference between the spun lace and a hydro-entangled product in general?
I'm not so much aware of the real technical differences, but basically it seems to be that on this spunlace you can't reach the same strength properties, and I think that's basically, you know, a lot to do with processing in mechanism in the production. That's by my understanding is the main difference.
All right. All right. Okay. Thank you very much, Dr. We have another question, and I hope that I'm going to be wording this question correctly. This is from Himanshu Agarwal. Is there any ASTM or any other standard tests that can be carried out on a filter for BV efficiency and kill rate test on a filter surface? On a filter surface. Does anyone have it? Want to stab at that one?
Well, this is John, and I'm one of the panelists. I think I can take on this question.
Okay.
Yeah, ASTM does have a test standard. I think it's ASTM 2101 for doing bacterial filtration efficiency and viral efficiency for respirators. Then recently, in response to the COVID-19 situation, we did a joint study with LMS. I think Albertini is also on the panel. We test several levels of the HVAC filters, MERV 5, MERV 12, 13, and 14. And we got viral filtration efficiency. And also we shared these results with the ASHRAE epidemic task force. They encouraged us to publish a paper. So we have a paper that's going to be published on the August issue of the HVAC journal. So basically, we found that, for example, with MERV 13 filters, you can achieve viral filtration efficiency close to 89%. With MERV 14 filters, you can achieve viral filtration efficiency close to 95%. So this LMS test method is kind of adopted from ASTM for HVAC filter testing. So the aerosol generation is similar to the ASTM. However, it's done in a much larger scale because the HVAC filters are much bigger at much higher flow rate. So there's no standard yet, but there's method for testing.
As an add-on, the ASHRAE has standard 185, which is the bioaerosol test for UV. You can use exactly the same procedures for a single pass HVAC test. You just can't call it a 185 if you're not using UV. But the work that was done 15 or 20 years ago by EPA, there's some publications out there for filters. So they've similar results to what John was saying, but there is a standard. It's basically just generate your aerosol by your bioaerosol and sample upstream and downstream. So with a lot more QA involved, but I believe that LMS is following essentially those same procedures, but just as an FYI that there is something you can quote as being essentially that already.
Can I explain a little better on this? My name is Albertini. One of the biggest issues with this viral testing and following ASTM is that it really doesn't differentiate based on the efficiency of the media as much. I mean, when we look at testing for masks right now, basically ASTM and NIOSH standards are partially good, but there's a lot of issue with this virus especially, and that's why the hospital staff and surgeons are dying. So in order to really do this type of testing, it has to be, it has to match the market that you're in. For the masks, for example, I mean, when you test it with high concentration, everybody's 99 point something. It really doesn't distinguish how good your filter is. It does, but not to that extent. So I really think we have to rethink the mask testing a bit, and also if you are going to basically help people to know how to protect themselves, modify the standards a bit to address that, we are looking with cumulative efficiency at this point. So it has to be done in a certain way to distinguish between a MER 12 and a 13 and a 14 and 11. So it's ASTM standards, but ASTM standards are very loosely written at this point.
Very.
We are seeing a lot of big issue in the market. And I really think we need to basically get to either directly virus testing or go to EN 1822 for most of the stuff.
One thing that's very helpful is that if you know the size of particle that your virus is in the air, your air filter already should have information on the efficiency at that size, and it ought to behave the same. One tricky thing with bioaerosol testing is depending on how you generate the aerosol, if you do it in water or broth or artificial sputum, you get different sized particles.
Correct.
So, and that affects how UV interacts with them, but it also affects how, the particle filter catches them because the size is a big difference.
Yeah, that's why you have to size the particles you are generating always. But in my mind, regardless of what size corona is, because I really don't know what size it is.
And that doesn't matter. It's the drops they're in that matters.
Correct. So for us is to challenge everything in the most difficult way. So if you are looking at viruses in general, I think 20 nanometers or 10 nanometers to 160 nanometers covers the range. So you have to generate your particles in that size. And it has been, we can't distinguish depending on how we set the concentration, but ASTM is too high of a concentration for really testing most of the regular filters. It's fine for testing the UV lights and all stuff, but when you get to non-woven pleated filters, it gets tricky if you go to very high concentration. You cannot distinguish between a 90% filter and a 99% filter.
Yeah. And a mask is also looking at right up next to the face. It's not looking at a drier aerosol like you would get in an HVAC system. Anyway, probably way more answer than you wanted for your question, but
correct.
Yes, there are ways to test it. No, there isn't an exact standard specified that you can call a specific number at this point.
But also for testing mask, I think virus is better because bacteria is big size. And the other thing is that, when we look at a lot of mask material, the MPPS is really different. It drops 20% sometimes from 95, 98 to 82%. So there are questions here that whether we really need to test the mask as it is, or can they come up with a better way to protect the hospital personnel, the doctors, because even like if let's imagine if the size of this virus is under 20 nanometer or 0.12, 0.15, then people are wearing HEPA filters as their mask, and the MPPS for that is right around there,
Okay.
So we have got issues here to really look at, and maybe the design should go to a hybrid glass fiber media for the mask. I don't know, but most of the standards right now, they're not really providing the data for protecting our frontline people at this point.
Okay. Well, it sounds like it's going to be an open issue for a while yet. So.
Sure.
We're trying to make it better, though.
Sure. Yeah.
Okay, well, that's good. I have a couple of more questions, and we're kind of running short on time. I just want to make sure we get to these other questions. I have a question here on what is the average cost and general process for obtaining FDA approval for a face mask? Do we have anyone that knows anything about that?
No.
Nope.
I mean, ASTM qualification it doesn't go through NIOSH. It can go through the labs. Mm-hmm. And it's the cost. The average cost is around $2,000 to do all of it, probably.
Okay.
Mitch, this is Bob Burkhead. I had a conversation with a customer yesterday that I asked this identical question, and they said you should be prepared to spend between $15,000 and $20,000 to finish your complete process to get approval at FDA. You know, the ASTM 2100, 2101, all that series of tests that are included in there are only a portion of it. There's at least 3 other things that need to happen. When you get it all done, you're going to have a bill that's, you know, well over $15,000.
Right. Well, I'm aware of what it takes to have a liquid cartridge filter certified by the FDA, or basically have their stamp on it, and it's significant. I would imagine it's going to be similar in the mass area.
It's going to be 100,000 plus.
Oh yeah, for sure. Yeah. So I have another question from Eileen. This question is related to airflow and pore size. And is there a relationship between the pore sizes and filtration efficiency and bacteria retention capability of masks? Basically, can the air perm be used as a regulator to for efficiency?
Can you repeat that question, please?
Okay. Out of curiosity, this customer is checking their filters with their porometer, and the pore sizes of MERV 13 filters and come out to an MPF of about 77 microns. While surgical masks have around an MFP of about 10 microns. Is there any kind of relationship between pore sizes and the filtration efficiency and / bacteria retention capability of the mask?
Well, this is John. My answer is that for mechanical filters, there's some correlation between the porosity and filtration efficiency, but not for electric filters. For charged filters, it's not behave that way. Because, you use electrostatic forces to capture particles. So basically, you can have very large pores, still very efficiently capture particles.
Okay. All righty. I hope that answers your question, Eileen. All righty. If we have no more questions, I'm sorry, go ahead.
No, I'm just mentioning, she said yes in the chat, in the Q&A bucket.
Oh, yes, I see. Okay, I didn't see that part. Okay, thanks, Bob. All righty, then I think that we're going to conclude this webinar. We're right on time at about 10:30. So I'd like to take this chance to recognize all of our Waterloo Filtration Institute members. Without them, we would not be presenting this webinar today. So I thank you very much. And also like to remind all of you that we do have a certified filtration and separation specialist program going on right now, in which we are currently in our liquid filtration stage. And we invite all of you to attend and check this out on our website. And with that, I want to thank all of our folks for all those who have attended. I want to thank you very much for attending. Thank you for your attention. And again, I want to thank all of our speakers and all of our panelists for your participation in this particular webinar. I appreciate it. I hope we can hear from you again. Thank you very much.